I'm Michael Bronstein. I'm a professor at Imperial College London and head of graph learning research at Twitter. And today I would like to talk about geometric deep learning.
Before we dive into geometric deep learning, let me start with a concept that is important in machine learning in general, and in particular in deep learning, which is inductive biases. Let's take a very simple neural network, a perceptron that is probably at least 60 years old. Basically, this is the simplest neural network that is possible. By connecting multiple such perceptrons in sequence, we get a multi-layer neural network that is called a multi-layer perceptron. And a very simple neural network of this kind is capable of representing a step function. Once we have a step function, we can represent any continuous function to any desired degree of accuracy. This is a property that is called universal approximation, and multi-layer perceptrons are extremely powerful in this sense that they can represent any continuous function to any desired accuracy. So this sounds like a good piece of news, but on the other hand, this is a very weak inductive bias. Basically, we don't assume anything about our input. And if we apply multi-layer perceptrons to images, for example, let's say an image of a digit that is stacked into a vector, we do not account at all for the geometric structure of this input data. So if the digit shifts in the input image, it will correspond to completely different vectors that will be fed into this neural network, even though we know and desire that this should be classified as exactly the same digit. A simple-minded neural network like this must learn what we call shift invariance from the data. And this will usually require a lot of examples and many parameters. The idea of using this kind of inductive bias that is good for image classification problems actually originally came from neuroscience, the famous experiments on the visual cortex done by Hubel and Wiesel that brought them the Nobel Prize in the 80s, and later implemented by Fukushima in the neocognitron architecture, and finally the classical work of Yann LeCun and collaborators on convolutional neural networks. They assume that the neural network is sparsely locally connected with shared weights. In this way, we can take advantage of self-similar structures at different scales, use local operations with shared weights, and we are able to obtain shift invariance by using shift equivariant convolutional filters. We'll talk in a few minutes about what is exactly meant by shift equivariance, interleaved with pooling operators that provide approximate invariance. From the computational side, what is important that the number of parameters per layer is fixed. It's independent on the input size, and the computational complexity is order of n. It's linear in the number of pixels in the image. Basically, going from multi-layer perceptrons, which are universal approximators, to convolutional neural networks that incorporate shift equivariance in their architecture, we can obviously extend these concepts. So there was a nice line of works from the group of Max Welling, extending shift equivariance to general group operations. The question is it the end of the story? And let's look at a very different kind of data. In this case, it's a molecular graph. So nodes represent atoms and edges represent chemical bonds. And let's say that we want to predict the atomization energy of this molecule. So how do we represent this kind of structure as an input to a neural network? Obviously, we can, as before, we can just say that represented as a vector. The problem is that here the order of nodes is completely arbitrary. So any permutation of the nodes will produce a different vector. And the neural network will need to be able to deal with any possible input. And these kind of structures, this kind of data appears ubiquitously in many applications, starting from social networks such as Facebook or Twitter graphs, different interaction networks, interactomes that are used in biology, functional networks in, let's say, brain imaging, and meshes, which are discrete manifolds that are used in computer graphics and medical imaging as well. So geometric deep learning is an umbrella term for deep neural network architectures that incorporate geometric inductive biases. So the term comes from a paper that I co-authored a few years ago, and there are other terms that are used in the machine learning community, such as relational inductive biases, graph neural networks, and graph representation learning. So the two prototypical objects in this field are manifolds and graphs. Manifolds are surfaces, they're usually discretized as meshes. Graphs are very basic abstract models of systems of relations and interactions. So today I will primarily focus on graphs, and I will say a few notes about the similarities and differences to manifolds. So if you look at images, which can be thought of as signals living on regular grids, and graphs, we see similarities and we see differences. So one of the differences, for example, that on an image, we always have a fixed number of neighbors. So each pixel has some adjacent neighbors. On a graph, the number of adjacent neighbors can be very different. Another difference is that the ordering of neighbors in an image is fixed. On graph, we don't usually have a canonical way of ordering the neighbors. And as a result, the very notion of invariance is very different. On images, we can talk about shift invariance. On graphs, we need to talk about something more general, such as permutation invariance. So today, I would like to describe and provide answers to three questions: how to generalize convolution-like filters, how to do pooling, and how to do all these efficiently. So let's start with the convolution, and allow me to take a step back and talk about convolution on grids first. So this is how a convolutional layer in a neural network looks like. Basically, each output is connected to a fixed number of inputs, and they all share the same parameters. So this way, we have sparsely connected neural network with shared parameters. If we write the weights of this neural network as a matrix, we can think of the mapping from input to output as matrix vector multiplication by a very special matrix that is formed by shifted versions of a vector of weights that is called W. Here, for simplicity and convenience of the analysis, let's assume that we have periodic boundary conditions. So this shift wraps around the signal boundaries. So this is called circulant matrix, and it describes convolution operations. We know that circulant matrices commute. Unlike general matrix multiplications, these are very special matrices. In particular, they commute with a special circulant matrix that is the shift operator that shifts the signal by one position. So this is what we call shift equivariance, which sometimes mistakenly called shift invariance. So shift equivariance, as the name suggests, means that it doesn't matter whether we first apply the shift and then convolution, or the other way around. Basically, in terms of matrix multiplication, it means that convolution and shift commute. What else do we know about commuting matrices? We know that they're jointly diagonalizable. So the eigenvectors of the convolution matrix will be the eigenvectors of the shift, which happen to be the Fourier basis, the good old sines or cosines. As a result, convolution is diagonalized by the discrete Fourier transform. So that's how we can do convolution in the frequency domain. We can first apply the Fourier transform, then multiply by the diagonal matrix, which also happens to be the Fourier transform of the coefficients of the filter, and then compute the inverse Fourier transform. There are two equivalent ways of thinking of convolution. We can do it in the spatial domain as multiplication by the specially structured circulant matrix, or compute the Fourier transform, do the pointwise multiplication of the Fourier transforms of the filter and the signal, and then the inverse Fourier transform. And these two ways are completely equivalent. So let's summarize so far what we recall from grids. Convolution in the spatial domain is a circulant matrix. You can think of it as local aggregation on adjacent nodes with shared parameters. This special structure is due to the underlying grid structure. And we know that all circulant matrices are diagonalized by the Fourier transform. which are eigenvectors of the shift. And as a result, we can perform convolution in the frequency domain by applying the Fourier transform, doing element-wise multiplication, and doing the inverse Fourier transform. Convolution can be computed efficiently. If it's a small filter, we can do it with linear complexity. If we use the Fourier transform, because we can do fast Fourier transform using the FFT algorithm, it costs us n log n operations, which is for any practical reason is almost equivalent to order of n. So let's see how we generalize these two graphs. So a graph, basically, it's a collection of nodes connected by edges. Edges are ordered pairs of nodes. These are directed graphs, or unordered pairs of nodes if the graph is undirected. We are also interested in the notion of neighborhood. So basically, these are all nodes that are adjacent to a node. Basically, they share an edge with a node, and the degree of a node is the size of its neighborhood. We are also interested in attributed graphs, so we can distinguish between node-wise features, which will be d-dimensional vectors attached to each node. We can arrange them into an n by d matrix, and edge features that can be attached to each edge in the graph. In the simplest case, we can just attach scalar weights to each edge. In this case, we say that the graph is weighted. The structure of the graph can be represented using an adjacency matrix, where each entry ij contains a non-zero value if there is an edge and the corresponding weight, and 0 otherwise. And if the graph is undirected, the adjacency matrix will be symmetric. We'll see in a second why this is important. Another important operation that we can do on graphs is what is called the graph Laplacian. Essentially, it's a kind of local difference operator. It subtracts from the feature at a node I the weighted average of the features in the neighborhood. And in matrix vector notation, we can write it as multiplication by these sparse matrix that we denote by delta. Here, D is diagonal matrix of the degree of the nodes, and A is the adjacency matrix. The way that you can interpret the Laplacian, it allows us to measure how smooth the signal is, how significantly it changes when I move from one node to another, basically how different it is from its neighborhood. And this is what physicists sometimes call the Dirichlet energy. It can be expressed as a quadratic form with respect to the Laplacian and tell us how smooth the features are on the graph. I should say that the Laplacian is really ubiquitous operator. You encounter it everywhere in mathematical physics. It can be defined on different structures. For example, on manifolds. In differential geometry, it's called the Laplace-Beltrami operator. And meshes are discretizations of two-dimensional manifolds of surfaces. So in computer graphics and geometry processing, usually the Laplace-Beltrami operator is discretized by this cotangent formula. So how do we do convolution on graphs? Basically, we've seen there are two ways. One is using the spatial domain formulation as local aggregation on adjacent nodes with shared parameters, and the frequency interpretation using the Fourier transform, which on graph will become what we'll call the graph Fourier transform. Let's again look at the Euclidean setting. So what is a one-dimensional grid? You can represent it as a graph, and if we assume that there are periodic boundary conditions, this is what is called the ring graph. So if we look at the adjacency matrix of this graph, we see that it's exactly the shift operator that we've seen before. So the recipe of doing spectral convolution on graphs is to use the eigenvectors of the adjacency matrix or the graph Laplacian as the analogy of the Fourier transform. The two are equivalent on grids because they're all circulant matrices and are all jointly diagonalizable. On graphs, the eigenbases will be somewhat different, but the idea will be very similar, if not the same. So if the graph is undirected, its corresponding adjacency matrix or Laplacian will have orthogonal eigenvectors. If the graphs are directed, the construction is slightly more elaborate and allow me to skip it for the sake of simplicity. On grids, the eigenvectors of the Laplacian or the adjacency matrix look like the familiar sinusoids, which is the classical Fourier basis. On general graphs, they will look differently, but if we order them by the corresponding eigenvalues, we can interpret the eigenvalues as frequencies. So the first eigenvector will be constant. It will be what the signal processing people call the DC component. And as we go to higher frequencies, we see more oscillations. in the eigenvectors. The simplest, straightforward way of generalizing convolutional graphs and convolutional neural networks is to parameterize the filter by its spectral coefficients. So the way that we compute convolution is applying the graph Fourier transform, which is multiplication by the eigenvectors of the Laplacian matrix, then applying the filter, element-wise multiplication in the with the spectral coefficients of the filter that are learnable, and applying the inverse graph Fourier transform, again multiplying by the matrix of the adjacency or Laplacian eigenvectors. Now, let's look at the complexity, and here comes the first piece of bad news. The complexity of computing graph Fourier transform is order of n squared. We need to multiply a vector by a dense matrix. There is usually no fast Fourier transform algorithm for graphs. And this is assuming that the eigenfunctions or eigenvectors are pre-computed, because if we account for the complexity of computing them, it will cost us up to n cube. Then application of the filter is linear, and the inverse Fourier transform is n squared again. So if you compare these to classical convolutional neural networks, in that case, we had order of n, in maybe worst case, n log n, which is almost the same. The number of parameters here is also order of n. Basically, these are all the spectral coefficients of the filter, as opposed to constant number of parameters independent on the input size. There is no guarantee of spatial localization. We're learning our coefficients in the frequency domain. Nobody can guarantee us that they are localized in the node domain of the graph. The resulting filters are isotropic, meaning that there is no preferred direction. I will talk about it in a few seconds. And filters are basis dependent. As a result, they don't generalize across graphs. So let's look at this example. So here we have, well, it's not a general graph, it's a mesh, but the idea is the same. So we have this coarse mesh, and on this mesh, we have a signal. It's ones in the red regions and zeros in the gray regions. And let me apply edge detection filter to this signal in the frequency domain. So I compute the Fourier transform, multiply element-wise by the coefficients of the filter, and compute the inverse Fourier transform. Now, what will happen if I even slightly deform this shape? You will see that the shape will change, the Laplacian will change, the eigenvectors will change. I keep the filter coefficients exactly the same, and the result of the filter will look completely different. So that's exactly what I mean by saying that it doesn't generalize across domains. Even very similar domains like this galloping horse will produce very different results. Let's now talk about the isotropy of the filter. And this comes from the fact that on grids, we can give names to our neighbors. We can order them in a canonical way. We can say that I have a neighbor on the left, a neighbor on the right. On graphs, we can permute and reorder the neighbors of a node in any way. There is no canonical way of doing it. So basically, any operation that we do on the graph must be locally permutation invariant. In a sense, there are no straightforward ways of defining directions on graphs. And if we talk about operations such as Laplacian, Laplacian essentially averages the neighbors. So averaging is a permutation invariant operation. And as a result, the filters that will be obtained from the Laplacian will be isotropic. They will be insensitive to direction. I should say that on meshes, we have a slightly different and more optimistic situation. We have more structure. Meshes are locally Euclidean. So here we still have ambiguity. We can choose the first vertex in any way we want. But after we made this choice, we can order all the rest of the vertices, let's say, in clockwise orientation. And in this sense, we, instead of permutation ambiguity, we just have rotation ambiguity. And this allows us to do, for example, anisotropic diffusion or anisotropic kernels on manifolds. So with this in mind, let's have a second take on the spectral convolution. And the different way of thinking of convolution on graphs is thinking of it as a matrix function that is applied to, let's say, the Laplacian. In this case, we interpret the eigenvalues of the Laplacian as frequencies and the matrix function as the spectral transfer function. And if we make this function parametric with fixed number of parameters, basically we have parameterized the filter with all one coefficients. If we make this function expressible in terms of simple matrix operations, such as matrix powers or matrix vector products, we can avoid the explicit computation of the eigenvectors altogether. We'll see it in a second. And it is also possible to guarantee stability under graph perturbations for some types of such functions. And it is also possible to guarantee localization, at least in some sense, either localization or exponential decay. So the simplest choice of this function is a polynomial, basically a polynomial of degree p, which has p plus 1 learnable coefficients, independent of the input size. It has efficient computation. Basically, with the way that we do it, we apply it to the Laplacian matrix, essentially taking powers of the Laplacian. Because the Laplacian is sparse, or the adjacency matrix is sparse, it has order of number of edges, non-zero elements. So multiplication by Laplacian roughly has linear complexity. So we don't need to do any eigendecomposition of the Laplacian. We just multiply by powers of the Laplacian. Another thing that we can guarantee that the filters are localized. They're localized to p hops, and this is because Laplacian works only on direct neighbors. So if I take the power p of the Laplacian, it will work on neighbors p times removed. So we can guarantee localization of the filters. We can also show that such filters generalize across graphs. They're stable under graph perturbation. And we can, of course, use this construction with different operators, for example, the adjacency matrix, and it doesn't matter if it's symmetric or not, because here we're not doing explicit eigendecomposition. So that was the analogy to spectral convolution. Let's talk about spatial convolution on graphs. And here again, take a step back and look again at the grid. And we've seen that the adjacency matrix of a grid is the shift operator. So if we look at the convolution, we've seen that it has this spatial circulant structure, essentially a multi-diagonal matrix where the elements on each diagonal are fixed. So we can decompose it into the powers of the adjacency matrix multiplied by different coefficients. So the convolution operation can be written as powers of the shift, a linear combination with some learnable weights. And we can take this idea to define probably the simplest convolution-like operation on graphs. So in this case, we're talking about vector node-wise features. We can arrange them into an n by d matrix, where each row represents the features of a node. And here in red, the features of one node are highlighted. So we can do two things to these features. We can transform them node-wise, in the simplest case by linear operation. Basically, this is right side matrix multiplication. And we can diffuse these features on the graph by basically averaging or combining features at adjacent nodes by multiplying from the left by a diffusion matrix, which can be the Laplacian, the adjacency matrix, or something like this. So this is how the simplest analogy of graph convolutional layer looks like. In this case, the learnable coefficients will be the linear transformation of the node-wise features. And we can concatenate multiple such layers by applying another graph convolutional layer to the output of the first one. So here is a simple two-layer graph neural network that allows to do node-wise classification. So to recap, we've seen, if we compare images to graphs, that in both cases we can do efficient local operations with linear complexity. The structure, though, is very different. In images, we have fixed number of neighbors, fixed ordering. On graphs, the number of neighbors can be different, and we cannot order them canonically. So all our operations are forced to be locally permutation invariant. So let's say a few words about pooling. Basically, in images, pooling is a reduction of the size of the image, usually by taking a patch of pixels and performing some operations such as maximum or averaging. On a graph, this would correspond to progressively coarsening the graph. One of the ways of doing it is by collapsing pairs of nodes along certain edges. So this creates a progressively coarsened sequence of adjacency matrices and coarsened features on the nodes of the corresponding graphs that can be done using the maximum. We can interleave convolutional and pooling layers like in standard classical CNN architectures, But here, the special thing that we can also make the pooling learnable. So the way that we collapse vertices together can be task specific and can be made in a learnable way. So far, we've been discussing convolution-like operations that are linear. We can think of it as a matrix that is parameterized by a certain number of parameters, like linear combination of powers of the Laplacian or adjacency matrix that multiplies the node-wise features matrix. So this matrix itself is linear. And this is how first graph convolutional architectures, such as ChebNet, graph convolution networks, or simplified GCNs looked like. We can make this matrix still linear operation, but dependent on the features themselves. So the features will be aggregated as a weighted combination, but the weights themselves depend on the features. And this is how popular architectures such as MONET or graph attention networks look like. So let me describe the MONET architecture, which was developed by my PhD student, Federico Monti. Basically, the idea is to produce some local charting around each node. And in this local system of coordinates, create a system of weights that can be interpreted as kind of soft pixels. So it's better to visualize it on meshes. There, the charting actually has geometric sense. We can use, for example, local geodesic polar coordinates. And then these weights act as a kind of soft pixels, which, for example, solves the problem that the number of nodes in the neighborhood of the node can be different. And finally, the most general recipe for filtering on graphs is a completely nonlinear operation that depends on X. And this is the very broad family where architectures such as message passing neural networks, edge convolutions, or graph networks fall. And let me describe message passing on graphs, or the edge convolution, how we call it. So basically here we have some functions that are computed using a pair of node features for nodes that are connected by edge, possibly also the corresponding edge features, and they're aggregating using a permutation invariant aggregation functions such as maximum, sum, or average. And you can use this kind of construction for point clouds where you don't have the graph, and you construct the graph from the features themselves by using k-nearest neighbors. It can be constructed on the fly, and it can be updated between layers. That's why we call this dynamic graph CNN. So this was architecture developed by Yu Wang from MIT, with whom I collaborated during my sabbatical there. So here's an example of how dynamic graph CNNs work on point clouds. So here the task is segmentation. So on the right, you see the supervision signal. And what we visualize here is the distance in the feature space of each layer from the red point. And you see that if initially it looks like Euclidean ball, then as we go deeper into the network, it becomes less and less geometric and more semantic. For example, it puts together the engines of the plane or the wings. So it becomes really specific for the given task. So in the remaining time, let me talk about applications. And as I mentioned already, graphs are very abstract mathematical ways of representing systems of relations and interactions. They can be used everywhere, but in particular in medical and healthcare applications, I would like to focus on 3 different structures from micro to macro, if you wish, starting with molecules, biological molecules that we can represent as graphs, interaction networks, such as interactomes, protein-to-protein interaction networks that can be represented as graphs, and finally, networks of patients. As with classical architectures, we have building blocks which we can combine into a single architecture that can be used to address different tasks. And several tasks that we can consider are node-wise tasks, such as classifying the nodes of a graph, classifying the entire graph, such as a molecule, and you would like to predict its properties, and autoencoder type of architectures where you want to embed the nodes of the graph, and from this embedding, for example, try to recover the structure of the graph. And this is typically used in recommender systems where you would like to predict edges between, let's say, 2 users on a social network. So probably one of the first applications of graph neural networks in the biomedical domain was the work from the group of Daniel Ruckert at Imperial College, where they tried to do disease prediction using a point cloud of patients built of imaging and phenotypic features. So the phenotypic features were used to construct a graph in a handcrafted way. And then on this graph, the imaging features were used for graph convolutions that transform these features and aggregated them from neighbors that represent similar patients in order to make node-wise prediction, the kind of disease that this patient might have. The key drawback in this approach is obviously the handcrafted construction of the graph. So with collaborators from Technical University of Munich, we extended this approach, introducing what we call differentiable graph module, where the graph is constructed on the fly. So basically we start with a point cloud of patients in high dimensional feature space, and we learn the right combination of features that should be used for construction of the graph, and another set of features that will be used as node-wise features on this graph, all optimized for the downstream task, which is, for example, node-wise classification. So here we show state-of-the-art results in tasks such as disease classification on the tadpole dataset or age prediction in UK Biobank. So let us talk about a different class of problems, and this is the problems from the domain of computational chemistry and drug design, where we represent molecules as graphs. So one of the key challenges in the discovery and design of new drugs is that the search space is humongous. We are talking about something like at least 10 to the power 60 of mid-sized synthesizable molecules, which is more than the number of atoms in the universe. On the other end, the number of candidates we can clinically test is probably in the range of hundreds or thousands. It's very expensive to conduct these experiments. So we have this huge gap between the number of possible candidates and the number of candidates that we can eventually test. And we need to bridge this gap by computational methods. So we can use quantum mechanical simulations to test how, for example, different molecules bind to their biological targets. We can use some simplified version of these simulations using what is called DFT, density functional theory. So graph neural networks sit above this in the sense that they can achieve the accuracy of DFT while being around 4 to 5 orders of magnitude faster. This was the work from DeepMind by Justin Gilmer already 3 years ago. And basically, this is a remarkable breakthrough for virtual screening of drug candidates. And graph neural networks have recently been used by a group at MIT that published their results in Cell earlier this year. They showed the discovery of a novel class of antibiotics where the virtual screening pipeline also included graph neural networks. Talking about drugs, another kind of drugs that we can think of are what is called biologics or biological drugs. Basically, these are drugs that themselves are biomolecules such as proteins. And one example where such drugs are extremely promising is cancer immunotherapy. What you see here is what is called the protein death ligand or PD-1, PD-L1 complex that is used in immunotherapy. And in fact, its discovery and description of this mechanism brought the inventors the Nobel Prize in Medicine in 2018. Basically, the way it works that we always grow cancer cells in our body. Normally, they're destroyed by our immune system, by the T cells. What happens in some cases that these cancer cells produce a protein that indicates to the T cells that these are healthy cells of the body. They are, as a result, are not destroyed. The tumor grows, and we get a problem. So the way immunotherapy works is by blocking one of these proteins. And as a result, the normal functioning of the immune system is restored, and cancer is no more treated as healthy cells and is destroyed. So the key problem here is how to design a binder that would match the target protein as a kind of a key that matches a lock. And that's exactly where geometric deep learning can help. So together with collaborators from EPFL, the group of Bruno Correa, we developed geometric deep learning methods that allow us to design proteins from scratch that would have certain functionality, for example, binding this cancer target. And this was a paper that appeared on the cover of Nature Methods earlier this year. So a different approach is let's abstract ourselves from the individual molecules and look how molecules interact with proteins in our body. And we know that drugs are designed to bind to their protein targets, and proteins in their turn bind to each other. So this can be described as a protein-to-protein interaction network or graph. So basically, by looking at different drugs, we can find what actually makes them drug-like. So we can take a data set of oncological drugs and train a classifier that will be looking at this binding signal on the protein-to-protein interaction graph. And this way, we have a predictor whether a molecule looks like anti-cancer or not. And now we can apply this classifier to molecules, for example, contained in food. And this is what we have done with collaborators from the Faculty of Medicine at Imperial College, Kirill Veselkov. Basically, we apply this classifier to food-based molecules, which allowed us to discover foods that are rich with cancer-beating or cancer-preventing drug-like molecules. And these champions, foods that contain many such molecules, we call them hyperfoods. And it appears that many boring foods like tea or celery or carrot are very rich with these molecules. So it's probably a good idea to add them into your diet, because this way you will be consuming chemicals, of course, maybe in minute quantities, that come from the same chemical classes as drugs that are used to cure or prevent cancer. Another application in drug development is what is called drug repositioning or combinational drug therapy. You know that it's very difficult to develop a drug, so why not repurpose existing drugs for different disease? And one of the ways of doing it is use combination of drugs. But the problem is that sometimes drugs, even completely innocuous drugs, in combinations, they react in such a way that produces sometimes extremely dangerous side effects. And in the US, we have about 5,000 FDA-approved drugs on the market. If we consider even pairwise combinations, we're talking about billions of different combinations that are absolutely impossible to test in a clinical setting. So here, graph neural networks can be used to predict the side effects of using combinations of drugs. That was very beautiful work by Marinka Zitnik, then at Stanford. She now joined the Broad Institute. And these ideas can be used also to find synergies between drugs. For example, if you want to find a cure against the COVID-19 disease caused by the novel coronavirus, we can look at drugs, combinations of drugs that together work better than each of them independently. Basically, some nonlinear synergy effects. Let me finish with applications from a different domain, three-dimensional shape analysis and synthesis. What you see here is a markerless motion capture system that is used in movie production in order to transfer the motion or expressions of an actor into this real-time animated 3D avatar. The system takes an input from a 3D scanner, and then it has to solve two problems. First is find correspondence between the noisy input and some canonical model of the face. And second, synthesize the new expression that corresponds to the input expression from this canonical face. And this way you get real-time animated avatar that looks like this green Shrek-like creature. So if we use geometric deep learning for these purposes, it's very appealing because we can incorporate deformation invariance in the problem by designing the filter on the deformable surface itself, as we've seen, as we can build convolutions on graphs and manifolds. And if in traditional convolutional neural networks, the result of the filter will depend on the way that the surface is deformed, if we consider it as a realization of some surface in three-dimensional space, in this case, the filter output will be independent no matter how the surface is deformed. We developed actually some of the first architectures for convolutional neural networks on meshes. We used them for finding correspondence between deformable shapes. So these are some of the state-of-the-art results that are computed by these architectures. We can also synthesize new shapes, so we can create a latent space that disentangles between a pose and identity. And you can see in this example, we have identity of one person with certain expression. We can subtract in this latent space the neutral expression, add a new identity, and then we get a new person with the expression of the first one. We can also use mixed architectures where the input is an image. It is encoded into the latent space using standard two-dimensional convolutional neural network, and then decoded by a geometric mesh convolutional neural network to produce a 3D model of the hand. And here you can see examples of how this works on images of hands in the wild. So you see that the prediction of the hand shape and pose is very accurate. This was a work by my PhD student, Dominique Coulon, in collaboration with a British startup, Ariel AI. And you can see here that it allows to build a 3D avatar, very detailed, with detailed hands and body shape that is actually extremely efficient and can be run on your cell phone. So to conclude, graphs are very general abstractions. They're useful everywhere, and deep learning models that are able to incorporate the structure, what we call relational inductive bias, are the right kind of learning architectures for these types of data. It is very cross-disciplinary research. I focused mainly for this talk on applications from the biomedical domain, where indeed there are many, but graph neural networks are nowadays used everywhere, from social networks to particle physics. It is a very hot field in machine learning. There are already several success stories where I can selfishly put the acquisition by Twitter of a startup company I co-founded with my students called Fabula AI last year. There are some first industrial applications and many, many open questions. So I think this is the right time and the right moment to use these methods for applications in medical imaging, in biomedical research, and healthcare. Last but not least, I would like to give credit to many collaborators with whom I have fruitfully been collaborating over the past years. And thank you very much.